Alrighty, hello. So we're going to do number 6 very quickly. So here it says, consider the graph of a degree 5. So keywords, degree 5. Polynomial shown to the right with x-intercepts at x equals -4, -2, 3, and 5. Okay, so because of this information, we can figure out what A is asking us to do. So right here, we can say that it says write a formula for a possible polynomial function. So it says possible, right? So because we have, remember, we have this degree, it's x to the 5th power. We know that at most it can have, so at most it can have 5x intercepts. Okay, so that's what that means. And then luckily, they already gave us those 5. They said -4, -2, 1, 3, and 5. Cool. So possible polynomial function that the graph represents using C as a constant factor. Now, don't forget that our factors are the binomials or monomials that we multiply one another with in order to create a function, okay? So here, I'm going to use a different color. We can identify our zeros here. So we have one at -4 again, one at -2. So you can see this on a graph. There's the other one at +1, and another at 3, +3, and then another at +5. Okay, so that way you can annotate your graph. So if you draw this in your notebook, you can see here that as long as you have your polynomial function crossing the x-axis, then these are the x-intercepts. Okay, so notice that none of these bump against the x-axis. They all go through it. So none of these have a multiplicity. They or of greater than 1. So all of these have a multiplicity of 1. So we're going to go ahead and write a possible formula using C as a constant factor. So we have a P of x. P of x is just some polynomial function, is equal to C times the factors of our zeros. So since x equals -4, the factor of that is going to be x plus 4. And then x equals -2, the factor of that is going to be x plus 2, and then so on. So we have x minus 1, and then for 3, we have x minus 3, minus 3, and then for 5, we have x minus 5. Great. So that is what we can do so far. Now the next step says, okay, suppose the y-intercept is -4. Okay, so this is another key information. So suppose the y-intercept, right, is -4. Adjust your function to fit the y-intercept by finding the constant factor c. Okay, so we need to find this constant. We need to figure out what is c. Okay. So then at this point, the y-intercept, so I'm going to write up here, it's going to be when x is 0, y is -4. Okay, so don't forget your coordinates are x and y, and since we're dealing with a function, this is your input and this is your output. Okay, so we'll go ahead and substitute this value. So we're going to substitute -4 into p of x, and then we're going to substitute 0 into every time we see x into our function. So I'm going to do that ahead. So I'm going to have -4 equals c times 0 plus 4, 0 plus 2, 0 minus 1, 0 minus 3, and 0 minus 5. Okay, so I'm going to simplify this now. We have -4 is equal to c times 4 times 2 times -1 times -3 times -5. Cool. And we keep going until we get this simplified further. So we can do this in our head. 4 times 2 is 8. 8 times -1 is -8. -8 times -3 is 24. And then 24 times negative 5 is 5 times 2 is 10. And then we have 12, negative 120. So now we have this whole thing is simplified to negative 120 times c equal to negative 4. Cool. So at that point, we still need to figure out what c is. So we're going to simplify further again and isolate the variable. We're going to divide by negative 120, divide by negative 120. And c is going to equal negative 4 over negative 120. When you divide both of these by 4, you're going to get 1 over 30. And that's your c value. Okay. So I don't have any space down here, so instead I'm just going to write my function up here. So I'll do that in different colors so you can tell the difference. I'll write it in blue. So we can say p of x is now, since we found out what c is, the constant factor of 1 over 30 times x plus 4 times x plus 2 times x minus 1 times x minus 3 and times x minus 5. Woo! Okay, cool. So that is our answer to option B. Okay, so right here, you'll notice this prompt is from your notes. And if you flip to the yellow page from your notes today that you received on Thursday, it says, what is the connection between the remainder when a polynomial p is divided by x minus a and the value of p of a? Okay, so what's the connection between the remainder, right? So in this case, what we can say is, we can say that if x minus a is a factor, then we can say the number, I'm going to abbreviate there or use a symbol, the number a is a 0 of p, is a 0 of p. Okay, so all that really means, so if you can have an example, so let's say we have x minus 3, right? So we have x minus 3 as a factor. Then we can say the number a, so in this case 3, is a 0 of p. And the way, you already know that. So if we set x minus 3 equal to 0, and you add 3 and you add 3, we get x equals 3. So we can say x equals 3 is a 0 of that function. Okay, and then for the last one, I'm going to use a different color. It says if p of a is equal to 0, then we can say x minus a is a factor of p. Okay, so all that's saying is when you substitute a value, so if I were to substitute 3 back into this function up here, then I should have, and I get that to equal 0. So if I do p of 3, and then I put it in my function, and then I do all that math, and I get 0, then I can say x minus 3 is a factor. Okay, so in this case, we have x minus 3, for instance. We already know that it's going to be a factor. I'm just proving right here, if we take the number, so in this case, it's just the 3. When we take the number a and substitute it into the function, and if we get 0 as our answer, then we can say, yes, that's a factor. Okay, so this case, before you had to do long division, before you had to do reverse tabular method, this is now another way for you using the remainder theorem to conclude whether or not a factor is indeed a factor of a polynomial. Okay, so go ahead, write your summary